Boom. Hello and welcome back to Calculus 3. We are back on our chapter 12 grind. We are going to look at 12.3, which is on limits and continuity. So last class, we defined a function that has 2D input and a 1D output, which is now in 3D. And now we would like to learn about the limits and continuity. So everything that we do in this section, again, will be upgraded from our Calculus 1. Except the limits now are going to be a little bit trickier, because in Calc 1, your input, your domain, was one-dimensional, which means that if you are looking for the limit, let's say x goes to 3 for x squared, when you look at the graphical approach for that particular limit, say this is 3, what you learned in Calc 1 is that if you approach from the left, you go up and then you go up to whatever this point is, and if you approach from the right, so those are those 3 plus and 3 minus, you would be pushing down into the point. So you see that you squeeze that squeeze all the values around that point 9, and since both of these point towards number 9, the limit is equal to 9. What's important is to understand that x-axis is one-dimensional, therefore your motion on that axis is only restricted to moving left or moving right. You can't go anywhere else. So you approach from the left, you approach from the right, which is giving the birth to that theorem that if the limit x approaches a from the left is the same as the limit of f of x where x approaches a from the right is L, then that means that the overall limit x approaches a is that L. That was the major theorem in Calc 1, and that's how we find all the limits or show that there is no limit. Now this theorem is going to be upgraded now for our 3D case. But there is one very important difference here. Your domain is now 2D. So what used to be your entire graph, now it's just the domain. So if I'm trying, let's say I have some function and that function did something, and I am looking at a point xy in the domain, and I am trying to see how that point works on the surface. So now this point here is xyz. In how many possible ways I can approach this point? And the answer is in infinitely many. You can approach this point at any angle. You can approach this point by spiraling in. You can approach the point using some kind of sine function that goes into it. There are infinitely many different approaches now, which kind of tosses this out of the window to prove the limit. We can't use this theorem anymore, or upgraded version, to prove the limit, because as you can see, you have infinitely many approaches. Earlier you only had 2 possible approaches, from left or from right. That's one-dimensional motion. Now on the xy plane you can approach in any way possible, and that is not possible to check. You know, when you only have two cases, like in Calc 1, you check both cases and you can make some theorems and conclusions. But now, with infinitely many approaches, you can't check them all. Because if I decide to go with sine 2x approach, you go, well, no, I'm going to do 2 sine x instead of sine 2x. And it's valid. So you have to worry about all of that. Definition of the limit is not going to change at all. But now we are approaching the neighborhood of the point, which is a disk that is around the point. And your epsilon and delta now are creating a 3D tubes that are wrapping around these values and trying to show what the z is equal to. So if you're missing still the concept of the limit, in a nutshell, the easiest thing to kind of understand is that limit is just a fancy way to compute the y value. In case of Calc 3, fancy way to compute the z value. Why do I call it fancy? Because it's much more powerful than just plugging the values in. Limit can determine the value at the point, even if the point doesn't exist, because the limit computes the values not at the point of interest, but at infinitely many points around points of interest. So that's why it's much more powerful than just plugging one value in and getting the answer. Well, sometimes that works, but in some cases it doesn't. So limit is a much more powerful alternative to that. So definition of the limit in two variables, we are going to use the same epsilon delta definition from Calc 1, except now we're just going to adopt it for Calc 3 using the two-dimensional domain. So the limit as x comma y goes to a, b of f of xy is equal to L if given any epsilon larger than 0, there exists delta larger than 0 such that, and then the same statement as before, f of x minus L is less than epsilon whenever 0 less than the square root of the distance formula, right? So x minus a squared plus y minus b squared less than delta. Oh, I just caught a mistake. This is x. This is a function of x and a y. Yes. The epsilon. Epsilon is the lowercase e in Greek. Oh, okay, yeah. Well, that's what I'm supposed to talk about now. All right. So what I'm going to do is draw again 3D coordinate system, and then we are going to have some kind of a function which is f of xy. Now this is supposed to be a 3D surface. It looks like a line only, but you know, imagine it that it goes places, all right? It's some kind of surface. Now, what we are going to do is we are going to pick the point on the xy domain, which around that point there is a delta. So this point over here is x, y, and around that point there is a disk of radius delta, and that is captured right here. Because as you can see, when you move that square root to the other side, becomes a square. What you get is the equation of the circle centered at A and B. So the coordinates of these points are A and B. Well, x and y are all points, and then these are particular ones because we are going to A and B. Oh, gotcha. So now we can run into this circle in any function that we want. Now, what's important to understand here is that this will go hit the surface somewhere and give us the z value back. Now what's happening is that this circle from down there is not going to be a circle on the surface because the surface is all curly, but it's important to understand that this disk creates this new shape that is on the surface, which maps into some sort of a range, and these distances here are epsilons. What I would like you guys to think about is exactly a tube. So there is some kind of a shape in space. There it is, shape in space. This is your f of xy. Now, this is the domain, and you pick a point at which you want to compute the limit. Shape is above that point, obviously, because point must be in the domain. What you do is you put radius delta circle around, which creates this tube going into the shape. And then that shape provides whatever kind of shape is going to follow the contour, right, on the surface. And that will give us the range for all z's that we could get, which goes onto the z-axis, which is the answer. The answer for this limit is z. So now, that's the epsilon. So the more you squeeze here to make the disk smaller, which is the approach, whatever way you want to, if the limit exists, these guys are going to squeeze. That's the same idea like in Calc 1. Nothing special there. The same, if you don't remember it, your textbook section 2.7 has that too, or go watch my stream from whatever I taught that. So it is the same idea like in Calc 1, except now we are squeezing a tube around. Earlier we had two parallel lines that squeezed into the line of interest. Now we have a tube around, and then depending on which approach you have. So now the limit as x comma y goes to a, b of some constant c is just c, because there is nowhere to plug in a and b. Yes?
What's the radius of that cylinder? What is that?
Delta.
Oh, it's delta.
That's the delta from, that's this delta from definition. That's that.
I just thought that was the long piece.
Well, luckily you have me, so you don't have to think. The limit of a constant is still that constant because there are no variables for your a and b to operate. Now, the limit when x and y goes to a and b, well, clearly x goes to a and y goes to b, of only x is going to be a. And finally, limit when x and y goes to a, b, of y is just b. So these x and y directions act as if they were independent of each other. Well, they are independent variables, but if you only have x in your limit, it actually becomes calculus 1 limit with just x goes to a. And if you only have y's, then it becomes y goes to b limit. Again, calc 1 type. So you can have these calc 3 limits with multiple domain, with two-dimensional domain to reduce down to calc 1 limits if the only values variables within the function are either x or y. And obviously for constant bypasses everything, yes. Constant. The limit of 9 is 9, regardless where these go.
So in this example, you kind of...
That is the only thing that exists, the plane. Like this ceiling is 10 feet tall, right? So we call it z equals 10. If I'm trying to find the limit of 10, it's 10. There is nothing else.
Also, the only value would be like that on top.
Yep. Because again, the limit is just the z value. Properties. So properties of limits, we have the same thing like in calc 1, except now we have to write much more because we don't have just x goes to a, we have x, y goes to a, b. All the properties are identical. So property 1 plus 2 states that the limit of, well, x comma y goes to a comma b of f plus minus g will be the limit of f plus the limit of g plus minus. This is both xy goes to ab and xy goes to ab. Number 3 is the constant multiple, meaning that you can kick the constant outside of the limit. That's again standard for all. So c times f, this is again y, you can kick the constant out in front of the limit. Number 4, the product rule for limits doesn't have a special formula, it's just you go straight through. So limit x, y, of f times g is the limit of f times the limit of g. I'm going to start abbreviating this because there's a lot of redundant writing. The limit of xy going to a, b of the quotient is going to be, every time I write f and g, it should be x comma y there, is the limit of f divided by the limit of g. Number 6 is the power rule. which says that the limit, again, xy goes to ab, of the function xy raised to some power n is the same as the limit of f everything raised to the n. So you can do the limit first and then you can exponentiate. This rule holds in Calc 1 as well. So if I'm looking for the limit x goes to 3 for x squared, I can just kick that square for the entire problem and just figure out what's the limit of x as x goes to 3, which is 3, and then square it and get 9. So either way. And the last rule is the fractional exponent. Which is the limit, again, xy goes to ab of f of xy raised to some m over n. Would be the limit m over n, provided that the n is not 0, right? Because you can't have that in the denominator. So rules of limits are identical as you know them from your previous math life.
Could you explain that the number 7 one again?
Well, instead of having x squared, now you have x to the 3/2, right? Which is the square root of x cubed.
Oh, so you're
It's
saying
just a fractional exponent.
Okay.
So you can just ignore it, you can do the problem and then exponentiate later. Good. Now we have to learn some terminology. So we are going to learn some terminology now about the limits at boundary points, but we first have to learn what are the interior points, what are the boundary points, and so on, so that we can use that notation. So interior point so these are definitions now of what it means for something to be interior point. So let R be the region in R squared, which is a 2D, and interior point P of R lies entirely within R, which means it is possible to find a disk centered at P that contains only points of R. Now you might be going, what the hell? If I have some kind of a region, needs to be smooth, Region R. Where is the interior point? Any point that I can locate so that I can draw a little disk around it. Now this looks like a potato, but it is some kind of a region R, and then each one of these points, it doesn't matter how close they are, you can always zoom in mathematics. If you're able to find a smaller disk which contains only the points of R, then that point is interior point. So each one of these little dots is a P value. And then you have a disk around it. Now this can have the radius to be as small as you want, beyond Planck length and all of that stuff. Mathematics, you can make it infinitely small. And now we're going to talk about the boundary point. So a boundary point Q of R lies on the edge of R in the sense that every disk centered at Q has at least one point in R and at least one point outside of R. Again, going to draw a different potato now. And if you pick a point on the boundary, which is on the line, when you draw a disk, you are able to locate the point inside and the point on the outside. So that's point Q. So no matter how close you get to draw the point on the inside, you will always be able to squeeze in a disk by zooming in, making the radius smaller. So even when I draw this and you say there's no way you can draw a disk around it, I can. Look at this. Boom. You make large, and then I take the thin one over here, and voila. See? There you go. Works. So it doesn't matter how close you get to the edge. If you are not on the edge, you will be able to draw a much smaller disk, right, than you usually would, and it will still be completely contained inside R, and that's interior point. But a boundary point that lies on the edge, when you draw the circle around it, the disk, you will always be able to find at least one point in and 1 point out. And that's what makes the boundary point. So these are definitions, because now we're going to talk about limits at the boundary point. So proving that the limit exists in Calc3 for these 3D functions, where you have two-dimensional domain, is not any easy task. And we usually use charts and graphs to do that, because the theorem approach from the left and approach from the right is completely useless in Calc3, because we have infinitely many approaches. So we cannot find the limit as easily as we did. So to show that the limit exists, and it's 7 or whatever it is, you actually have to do the chart of values pick a whole bunch of numbers that lie within that disk, right, with different x and y values, and then hopefully they all point towards the limit, let's say 7. But when you are at the boundary, the things change, and at those cases, right, we might easily have limit not to exist. And what we do is we can use the theorem that we cannot use to show the limit. We can use that theorem to show that there is no limit. Because if you are able to find two different paths that give you two different values for the limit, that means the limit doesn't exist. So the theorem still holds in Calc 3, except it's not practical to prove the existence of the limit, but it is very practical and very efficient to show that the limit doesn't exist. And that's exactly what we are going to use it for. We are going to recast this Calc 1 two-approach theorem into Calc 3, where we again say if we can find two different paths that give us different limit, then the limit does not exist. Now, you also should remember at all times that you used algebra in your Calc 1 to solve some limits. So just to refresh your memory, if you had to solve the limit as x goes to, let's say, 5, and you had x minus 5 over x squared minus 25. The way you solve this limit is you used algebra. You factor the denominator, right? And then you cancel what you can. And this becomes now limit x goes to 5 of 1 over x plus 5, which is 1 over 10. So we were able to compute the limit using algebra. Now we might be able to do the same. Well, some limits will just be, plug and pray. That's easy. For some, you will have to massage with algebra a little bit to solve. And then for some, you will just use the theorem to disprove and say there is no limit because I'm able to find two paths which end up with different results and so on. So here is the exercise. It says, so this is Calc 1 review. And now here is the Calc 3 question. It says limit as xy goes to 0, 0. And you have x squared minus xy over x. So clearly you can't just plug in the value and get number because it's divided by x and x goes to 0. So technically you are dividing by 0. We are not allowed to do that. But with careful observation, you see that algebra tells you to factor out x and then they cancel. Once they cancel, now you have just 0 minus 0 and you can show that the limit is 0. So it's the same, or if you remember your limit definition for the derivative when you had divided by h and you did all the different types of witchcraft to get rid of it. So you are remembering now that rationalizing plays the role, adding fractions and clearing out double fractions plays the role, factoring and canceling play the role. All of those basic algebraic techniques which you guys used earlier, they still are all available here. And then sometimes problems are just spicier. Usually I don't do problems from the textbook, but you all have ability to read, you know all the letters and stuff. I hope. But here is the one that it's worth looking at. You see, when x goes to 4 and y goes to 1, if you compute this, you get 0 in denominator. So that means it's a boundary limit. That means some algebraic manipulation has to take place. Now, what would that be? What algebraic manipulation might be appropriate for this case, and why? Correct. It's called rationalizing, and when you have square roots, you try that. Now, it doesn't matter whether the square roots are in the numerator or in the denominator. Try rationalizing either way, because you're hoping for stuff to cancel. You need to change the shape of the denominator so it's not 0 once you plug in 4 and 1. So as Evan said, we are going to go square root of x plus 2 root y. This is called a conjugate. And then you have a lot of algebra to clear. So I'm not going to multiply this. I'm just going to say, leave it like this, because maybe it cancels as a whole. Now, in denominator, what I have is x times x minus 2y. No, 4y. Minus 4y. Oh, you look at this. When you, from the first parenthesis, when you kick out y, this is why you're not supposed to multiply. You wouldn't be able to see it. Over here, kick out 1y, and you get exactly this, and they cancel. Problem solved. So now, in the next step, you have to write this limit every step, otherwise -1 per step per problem. That's going to be like the final grade on the next test, like -3 or something, if you forget your plus c's and you forget your limits step by step. So you kick out y, and you are left with x minus 4y, and you still have your root x plus 2 root y divided by x minus 4y, and this is where they cancel. Done. So now you are allowed to plug in values and quickly obtain the limit. So y is 1, we don't have to worry about that. That's 2 plus 2, 4. Because as soon as you cancel this denominator, you are allowed to plug in values and compute. So the limit is 4. The next concept is non-existence of the limit. And the concept after that is continuity. Yeah, we're staying till 11:30, I know. That one? All right. So now we are going to use our theorem. I'm not sure if they actually stated the theorem. Yeah, they did. They call it a procedure. So if f of x, y approaches two different values as x and y approaches a, b along two different paths, the domain then limit does not exist. So if fxy approaches two different values, as xy approaches a, b along two different paths, then limit of f of x does not exist, dne. That's what I said. Please pay attention. Right. So this begs for an example. Well, that's what we're going to do now as in the example so we can understand that part. Problem 27 says limit x and y approaches 0, 0. And we have x plus 2y divided by x minus 2y. So the first thing that you will do in Calc 3 is the same as Calc 1. And that is you try to plug the values in. If you get a number, you're good. If you have 0 in denominator, no good. We have to do something. So we start by trying to plug in, and we see that denominator gets 0. So therefore, I can't use the most basic technique, which is plug in. All right, so I'm going to try and disprove this limit by picking two different paths and computing limits. As soon as I reach a value that is not the same as one of the previous values, immediately the limit does not exist. So I will try here, and here is the answer to your question. What do you mean two paths? I'm going to try a path y equals x. Now what does that mean? Observe that we are approaching the origin, and I am picking y equals x approach, which means that I am approaching now this way. So as soon as I say let y equal x, my limit becomes x goes to 0, and every y will be replaced by x. Therefore, what I'm getting is x plus 2x divided by x minus 2x, which is further limit of x goes to 0. I have 3x divided by negative x, and this becomes negative 3 because x's will cancel, and you are getting negative 3. So now what I'm going to do is I'm going to choose a different path. Say let y equal x squared. Now that path looks like this, and I am approaching like that. Do you understand now what the different paths mean? I pick a function along which I'm going to walk on the domain towards the point that I'm looking that I picked to look at the limit. So now the limit x goes to 0. Again, I am eliminating all the y's. So I'm getting x plus 2x squared divided by, and on the bottom I have x minus 2x squared. So we clear algebra, see what we can get. I can factor out x on top and get 1 plus 2x, and I can factor out x on the bottom and get 1 minus 2x. Now these x's will cancel, and I hope you guys see that when x is equal to 0, you get 1 over 1, which is the limit is 1. But the other approach told us is negative 3. See that? Now what does that mean in space? So say that my goal is to reach this thing. It's right there. Now, if you understand what it means, you know that your xy plane, which is the floor, has the coordinate, whatever, 20 and 1, right? 1 foot this way and 20 feet that way. So 120, let's say, is where the object is at 9 feet. So this is going to be 1, 20, 9. That's the location, right? The limit is that 9, the height at which the object is. Now, this limit is 9 because if I approach from this end, the limit is 9. If I spiral in towards it, right, like that, it's going to be there at 9. It's always 9. What we calculated here is that if I approach y equal x, which is diagonally in the classroom, the object is -3, which means below the floor, and then like 3 feet below the floor. And if I approach with the x squared, which is parabola kind of walking, the object is 1 feet above the floor. You see how it doesn't make sense? The object cannot be at 2 locations at the same time, unless you're electron, but quantum mechanics aside. So the existence of the limit is you can think about physical things, and this is z equals -3, and this is z equals 1 at the same point, right? So if I approach from different, with different paths, I end up at a different height, which makes no sense. If there is a limit, it has to be always the same number. So as you can see, theorem is very, very useful for us to prove that. Now, I can also try to solve the same problem using a very interesting trick, and that is try infinitely many approaches at once. Yes? Well, when I choose the approach, either x or y will survive here, and they have to be whatever you are approaching. And the function that you are using must include that point. You can't be approaching origin using y equal mx plus b that doesn't pass through origin, right? Because at that point you are not approaching the value. Now, I'm going to write the same problem. Limit xy goes to a, b of x plus 2y, x minus 2y, and I'm going to use the path y equal mx. Now, mx is definitely passes through origin, so it passes through 0, 0. But look at this m. M is a parameter. So technically, I am checking for x and 2x and 3x and -7x, right? So I am approaching the origin from any possible direction there is. So I'm checking all of these approaches at the same time. This is my x, this is my y. And these are all m slopes. All of them, positive, negative, halves, and negative pi, and so on. Yes?
If you were given any other value for AB, like, I don't know, 16,
-3.
-3, sure.
You will have to find the line which satisfies that point.
Right. In the y equals mx plus b form, right?
Yes, and x squared form, and sine x form, and e to the x form.
Right.
Yeah.
I'm just saying, could you pretty much just use the y equals mx plus b form for
Everything.
any of these? Right.
Well, now I'm using y equal mx, which is actually infinitely many approaches at once. So let's see what happens. x plus, now y is mx, so 2mx divided by x minus 2mx. Right, all the y's are replaced by mx. I can factor out and cancel x's. No, I wanted to use 0, 0, same problem, sorry. 0, 0 here. I'm solving the same problem. And look what happened. The limit is 1 plus 2m divided by 1 minus 2m. Limit depends on m. So if I pick 3, this is going to compute to a certain value, and if I choose 4, it's going to compute at a different value. So you see by this one calculation that we show infinitely many approaches at once. If your limit ends up being dependent on m, that means that every single one of these approaches will give you a different value. So this is a very quick way. Does it work all the time? Hell no. Right? It's not going to work all the time. Sometimes you will have to figure out a different type of a function. So we just used infinitely many linear functions to approach, and we found infinitely many different limit values. So good. We're good to find 2 only, but by 2 numbers that are different than each other. And what I found there is infinitely many at one shot. So, you know, for some problems you try, and if you don't get your limit to be dependent on m, that means that all of the linear approaches will return that value. That limit could exist at that point. Then you try quadratic, try exponential, 2 to the x, or e to the x. So you try, or if you need to go to the origin, would be e to the x minus 1 to put it down to go to the origin. So there's a lot of different functions and approaches that you can make. The last thing that we have to just mention, it's the upgrade from Calc 1 is continuity, and we're done. Continuity at the point. Let's say P of P of xy. So what do I have? Number 1, f of AB exists. Limit of f of xy exists. That is as x and y go to AB. And third and final, limit of f of xy is equal to f of AB. As you can see, same as Calc 1. As xy approach AB. 3 rules to establish continuity at a single point. And then we have the global continuity, which states the function, no, actually just not the function, f of xy is globally continuous if it is continuous at every point in its domain. So the global continuity rests on the shoulder of the point continuity. And if you are able to show that, now there are infinitely many points there, right? If you're able to show that the function is continuous at every single point, then the function is globally continuous everywhere. And calculations for this are the same as in Calc 1. You check that the value is defined. You take the limit C that exists and just check the third rule by making sure that the numbers you got in 1 and 2 are the same. At which point the function is continuous at that point. Then you redo all procedure for the next point and the next and the next and so on. And that takes care of this part. I'll answer any questions since we are running a little bit late, right? And I had to rush through definitions for continuity and no example and so on. If you have any questions, we'll start with that tomorrow and then go through 12.4 and 12.5. I will see you all tomorrow. Ciao.